This is going to be the first part of our electricity unit. This is going to start talking about electric current. Okay, so electric current is the continuous flow of charges through a material. Okay, before we had studied about the different types of energy. Electricity was one of those types of energy. It's this energy of electric charges. So we know that then electric current is the continuous flow of electric charges through a material. Okay. The amount of charge that passes through the wire in a unit of time, it is the rate of electric current. The unit for the rate of current is the ampere or amp, or simply it could be just the letter A. Okay. The number of amps describes the amount of charge that's flowing past a given point each second. Okay. So in your book, you would see that there is a picture of a conveyor belt full of tomatoes, and the picture is trying to help you understand that the conveyor belt is more like your electric circuit, okay, the wires in your electric circuit, and that the tomatoes are your electric charges, your electrons. So when you see that there's a person that's standing there that's kind of checking out how many tomatoes go past that certain point per second, that's exactly what your ampere is that it's how many of those tomatoes are going past that particular point every second. So in this case, though, with your electric circuit and your electric charges, it's how many electrons are going to be flowing past that point every second. Now, there's a need for a circuit because your electric current doesn't automatically exist in a material. Okay, so your electric current does not automatically exist in a material. And you might notice that there's other types of electricity, like static electricity, where it has just charges that will discharge automatically. Okay, there's no path to them. And with static electricity, you don't have that current. So needless to say, electric current does not automatically exist in that material. Current requires a specific path to follow. And the charges must flow continuously from one place to another in order to produce your electric current. So current requires an electric circuit. An electric circuit is a complete, unbroken path through which electric charges can flow. Okay, so let's take a look at your racetrack down here. This is a good analogy for a circuit. Okay, the racetrack itself, that's going to be representing the circuit, a complete unbroken path. Okay, but your little race cars, that's going to represent your current. Okay, you can think of it as your car rent. Because your cars, like at a NASCAR race, would continuously drive around that track. Okay, and as long as it's closed, the cars can go through. But if there's spot that's missing, well, can your cars go through then? No, they wouldn't be able to continue on their path. So only closed paths or closed loops are going to allow your current to continue to flow. Okay, so our next part is going to be talking about conductors and insulators. Okay. A conductor transfers charge, electric charge well. Okay, a conductor is a material through which charge can flow easily. Within a conductor, which could be any type of metal, and metals we know are elements found on the periodic table that we studied earlier this fall. So we know that any of these metals would have atoms unique to that particular element. And what buzzes around all of our atoms? Well, enraged Elliott electron. So in these conductors where a charge can flow through easily, electrons are bound loosely. And these conduction electrons are able to move throughout the conductor. An electric current is then formed as the electrons flow through the conductor. Now, how does the light turn on the instant you flip a switch? Well, electrons are not sent to your house the instant you turn on the switch. They are already present inside the conductors that make up the circuit. So they are already present inside the conductors that make up the circuit. When you flip the switch, electrons at one end of the wire are pulled. Okay, so it's going to be pulled out of that outlet. Okay, while those at the other end are then pushed. So the result is a continuous flow of electrons through all parts of the circuit as soon as the circuit is completed. Okay, so from your outlet, if you plugged in something like a lamp, you would have the hot slot, which is the shorter part of your outlet. Okay, it would be going up through the copper wiring and then across your filament in your light bulb. And then it's going to be pushed down the other side of your cord and then back into the neutral slot of your outlet. And that has to happen for it to be able to form a closed and complete circuit. Now, some examples of conductors include metals such as silver, copper, aluminum, and iron. Okay, so we know that conductors allow electrons to flow through easily, but insulators are just the opposite. Okay, so an insulator does not transfer electric charge well. An insulator is a material through which charges cannot flow easily. The electrons in an insulator are bound tightly to their atoms and do not move easily. Your electrons are not going to be able to get through that insulator. So why don't you get a shock when you touch a cord? Well, a cord carries charges from an electrical outlet to an appliance. Okay, the inner wire is the conductor for the current. The rubber coating around the wire is an insulator. Okay, the cord then allows charge to continue to flow to the appliance, but stops it from flowing into your hand and shocking you. This is just an extra line. Sorry about that. Okay, so what are some examples of some good insulators? That would include rubber, glass, sand, plastic, and wood. Okay, so those all are examples of insulators where the charges do not go through very easily at all. Okay, we're going to stop here for our first section. We're going to continue with our second section on voltage, resistance, and electrochemical cells. Thanks for listening.